始めます。テキストはここにあります。それで、これを15ページ。15ページ。AC16 ページから AC Electrical Conductivity of Metal。それで、ちょっとやってみようかな。これはなんか直すとこあったっけ。これは OK。パート6。これ OK ね。はい。まず YouTube リンクは、正しいかな。Electrical Conductivity。正しいかな。3分前に、これなんか違うな。ページが間違ってる。後で直そう。ページが間違ってるので、後で直します。それで、ブルーキャット。4時から5時、3月11日。第7回第1章、パート7。第1章、パート7。OK ですね。それから、コンパス。007。時間が間違ってる。時間が間違ってるので、これでいけます。パート7。それから、テキストはここにあります。OK かな。閉じる。閉じる。ということで、AC Electrical Conductivity of a Metal. To calculate the current induced in a metal by a time-dependent electric field, we write the field in the form electrical field as a function of time is real part of E omega E exponential to minus I omega t. The equation of motion 112 for the momentum per electron becomes like this. dp dt is minus p over tau minus e. We seek a steady state solution of the form p of t is real p omega exponential minus I omega t. Substituting the complex p and e into 1.24, which must be satisfied by both the real and imaginary parts of any complex solution. I don't know why. Which must be satisfied by both the real and any complex solution. We find that p omega must satisfy this one. I omega p. Let me see. I omega p omega minus I omega p omega equal minus p omega divided by tau minus e omega. since J equal minus NEP divided by M, the current density is just J of T is real part of J omega times e to the power minus I omega t, where J omega equal minus NEP of omega divided by M equal I think this one, I think this is solved, right? This guy is more like tau 1 over tau minus I omega P of omega equal minus E omega. So P of omega equal 1 over tau minus I omega minus E of omega. And so we just substitute this one, right? We substitute this P to this, to here. Then we obtain this one. This is a little bit strange. So this guy is a complex number. This is a complex number. Okay. And the question is whether this guy is complex or not. So this is also complex. We write the electric time-dependent electric field. We write the field in the form. So this is also a complex number. And this is also complex. I would say. Is that right? Substituting the complex P and E into 124, which must be satisfied by both the real and imaginary part of any complex solution. We find that P of omega must satisfy 1.26 since J equal minus NEP divided by M. The current density is just J of T is real part of J omega exponential minus I omega T, and J omega is like this. So you can see P is complex here. P is complex and E Actually we can assume E of omega to be real, maybe, but P of omega is complex, and J of omega is also complex. Or customarily, right? One customarily writes this result as J of omega equal sigma of omega E of omega, and this one is also complex. Where sigma of omega, known as the frequency dependent or AC conductivity, is given by sigma of omega equal sigma 0 divided by 1 minus I omega tau. Note that this correctly reduces to the DC Duluth result 1.6 at zero frequency. The most important application of this result is the propagation of electromagnetic radiation in a metal. It might appear that the assumptions we made to derive 1.29 would render it inapplicable to this case. It might appear that the assumption we made to derive 129 would render it inapplicable to this case, since the electric field in an electromagnetic wave is accompanied by a perpendicular magnetic field H of the same magnitude, which we have not included 124, and the fields in an electromagnetic wave vary in space as well as time, whereas equation 112 was derived by assuming a spatially uniform force. The most important application of the result is to the propagation of electromagnetic radiation in a metal. It might appear that the assumptions we made to derive 129 would render it inapplicable. I don't know. Render, if it is this one, inapplicable to this case is propagation of electromagnetic, maybe this. Since the E field in an electromagnetic wave is accompanied by a perpendicular magnetic field H of the same magnitude. Footnote 20. One of the more appealing features of CGS unit. Anyway, which we have not included in 124, and the field in an electromagnetic wave will vary in space as well as time, whereas equation 112 was derived by assuming spatially uniform force. The first complication can always be ignored. It leads to additional term minus EP divided by MC cross H in 1.24, which is smaller than the term in E by a factor V over C, where V is the magnitude of the mean electric velocity, interesting. So in CGS, E and H are same, but the contribution to the force, contribution to the acceleration is reduced by factor V over C, where V is the magnitude of the mean electronic velocity, but even in a current as large as 1 amp per square millimeter, V equals J divided by NE is only of order 0.1 centimeter per sec. Hence, the term in the magnetic field is typically 10 to minus 10 of the term in the electric field and can quite correctly be ignored. The second point raises more serious questions. Equation 1.12 was derived by assuming that at any time the same force acts on each electron, which is not the case if the electric field varies in space. Note, however, that the current density at point R is entirely determined by what the electric field has done to each electron at R since its last collision. This last collision, in the overwhelming majority of cases, takes place no more than a few mean-free paths away from R. Okay. Note, however, that the current density at point R is entirely determined by what the electric field has done to each electron at R since its last collision. This last collision, in the overwhelming majority of cases, takes place no more than a few mean-free paths away from R. Therefore, if the field does not vary appreciably over distances comparable to the electronic mean-free path, we may correctly calculate J of RT, the current density at point R, by taking the field everywhere in space to be given by its value E of RT at the point R. The result, J of R omega equals sigma omega times E of R omega, is therefore valid whenever the wavelength lambda of the field is large compared to the electronic mean free path L. This is ordinarily satisfied in a metal by visible light whose wavelength is of the order of 10 to 3 to 10 to 4th angstrom. When it is not satisfied, one must resort to so-called non-local theories of greater complexity. Note, however, that the current density at point R is entirely determined by what the electric field has done to each electron at R since its last collision. I don't understand this. The current density at, okay, this is not electronic density, this current density at point R is entirely determined by what the electric field has done to each electron at R since its last collision. Okay, the last collision in the overwhelming majority of cases takes place no more than a few mean-free paths away from R. Therefore, if the field does not vary appreciably over the distances comparable to the electronic mean-free path, we may correctly calculate J of RT, the current density at point R, by taking the field everywhere in space to be given by its value E of RT at the point R. The result, J of R omega equals sigma omega times E of R omega, is therefore valid whenever the wavelength lambda of the field is large compared to the electronic mean-free path L. This is ordinarily satisfied in a metal by visible light whose wavelength is of the order of 10 to 3 to 10 to 4 angstrom. When it is not satisfied, one must resort to so-called non-local theories of greater complexity. Assuming then that the wavelength is large compared to the mean-free path, we may proceed as following. In the presence of a specified current density J, we might write Maxwell's equation as divergence of E equals 0, divergence of H equals 0, curl of E equals minus 1 over C partial H partial T, curl of H equals 4 pi divided by C times J plus 1 over C partial E partial T. We look for a solution with time dependence exponential minus I omega t, noting that in a metal we can write J in terms of E via 1.28. We then find curl of curl E equal nabla square E equal How come does this nabla square E anyway? I think this jumps. This goes here. Then this go to this, and this go to this. Where J and E are related. This J go to this go to here. Yeah. Or if we summarize this one, this has the form of the usual wave function, wave equation, usual wave equation. 本当だね。マイナスナブラスクエア E equal オメガスクエア divided by C square epsilon omega times E with a complex dielectric constant given by E of omega equal 1 plus 4 pi I sigma divided by omega. If we are, so let me read the footnote 21. We are considering here an electromagnetic wave in which the induced charge density rho vanishes. Below, we examine the possibility of oscillations in the charge density. Let me see, what's that? 21. In the presence of specified current density J, we may write Maxwell equations as we are considering here an electromagnetic wave in which the induced charge density rho vanishes. Below, we examine the possibility of oscillations in the charge density. I don't understand. We are considering here an electromagnetic wave in which the induced charge density vanishes. Here, but below, maybe we examine the possibility of oscillations in the charge density. Not here, but below, maybe. Below, does this mean next page? I don't know. Below, next page. Anyway, if we are at frequencies high enough to satisfy omega tau is much larger than 1, then to a first approximation, equation 1.35 and 1.29 give 1 minus omega p square divided by omega square. Where omega p, known as the plasma frequency, is given by this. Let me see. For small omega, epsilon is 0. Epsilon is 0. Small omega if frequency is high enough, okay, let me write it down. I think sigma has to be ne squared tau divided by n. No, confusing. Sigma of omega. Is it sigma of omega? This one? Is it this? Omega 0 divided by 1 minus I omega t. This is sigma 0 divided by 1 minus I omega t. This way. Omega t or omega tau. I got confused. See, this is tau, maybe. I omega tau. Okay. So then if this is very high frequency, we can 4 pi I, okay. 4 pi I, then omega here. If omega tau is much larger than 1, we can ignore this one. Then we can cancel tau, can cancel I. Yeah, then this will be 1 minus omega square times m 4 pi ne square. If omega is large, four pi ne square over m. That's a plasma frequency. Where omega p, known as the plasma frequency, is given by this. When epsilon is real and negative, hey, how do I write 1 minus negative omega 0 is small. The solution to 134 decay exponentially in space. No radiation can propagate. 1.34 decay. However, when epsilon is positive, the solution to 134 become oscillatory. Radiation can propagate, and the metal should become transparent. This conclusion is only valid, of course, if our high frequency assumption 136 is satisfied in the neighborhood of omega equal omega p. If we express tau in terms of the resistivity through equation 1.8, we can use the definition 138 of the plasma frequency to compute that omega p tau I think we should do this way. So here, from here, I think we can do omega p tau square is this range. 4 pi. This should be 4 pi m 分 m ne square tau times tau, and this guy is sigma 0. Then how can we convert it to this? Very strange. Maybe. Okay, so I can convert it like this. Omega p square tau is like 4 pi sigma 0. Then omega p tau equal 4 pi sigma 0 divided by 4 pi ne square n. Yeah, so 4 pi is cancelled. Then I don't know how to cancel e square. Since the resistivity in micro-ohm centimeter is the order of unity or less, that's okay. And since Rs over A0 is in the range from 2 to 6, the high frequency condition 1.36 will be well satisfied at plasma frequency. I don't know if I'm getting the unit right. Let me try again. I can do this way. Omega p tau is like omega square tau divided by omega p. Okay, so I can do this square root here, square root. Yeah. I think this unit is screwed up. This is not, this guy is, this has some dimension. This is like a micro ohm centimeter inverse. This has some dimension. Then this is dimensionless. This is dimensionless. Sorry. This is dimensionless. Then this guy has dimension of micro ohm centimeter. This 1.6 times 10 to 2 has some dimension, because left hand side, this is dimensionless. This is mystery. Sorry, I don't know if this is working. Since the resistivity in micro ohm centimeter rho mu is of the order of unity or less, and Rs divided by A0 is in the range from 2 to 6, the high frequency condition will be well satisfied. I think 36 is this one. Omega tau is larger than omega tau is larger than 1. This is satisfied, will be well satisfied at plasma frequency. Okay, maybe let's stop here. This is what page? 18. We start from page 18 next time.